Hello everyone, and welcome to this your first lecture in your physics course. In chapter 1 we're going to be dealing with units and measures. If we take a look at what you need to know after this section, you need to familiarize yourself with the prefixes for what we call the SI units, the standard international units. Then you also need to be able to do order of magnitude calculations, which are a form of an estimate calculation based on some assumptions. And then finally, you need to be able to solve problems on the above two concepts. Let's first talk a little bit about what physics is. Well, physics is one of the foundations of the sciences. I would say physics and maths together form the foundation of the other sciences. This is to say that in physics, we're concerned with the fundamentals of the universe, the building blocks of the universe. We would like to understand how everything works, everything from the smallest atom to the largest galaxy. Physics can be divided into a number of different areas as shown. There's classical mechanics, relativity, thermodynamics, electromagnetism, optics, and quantum mechanics. In this course, we're mainly going to be focusing on classical mechanics as well as thermodynamics. If you're looking for some inspiration as an engineer, as a physicist, as a scientist, we can look to Elon Musk. He's actually South African, and many of you will know of him. He's the founder of multiple companies, including SpaceX, which is a company that looks into building reusable space rockets to make space exploration feasible and possible, as well as Tesla, which is a very successful electric car company. Here's an interesting interview from a few years ago where Elon Musk was asked, out of all the courses that he did at university, which does he think is the most useful? Let's listen to his answer.
Another question about what kind of physics course do you like most? Which physics course do you think most helpful for your company, for your creative thinking, for your so wonderful companies?
Sure. Actually, the fundamentals of physics that's what's most helpful. The very framework of how to think about physics is by far the most helpful. And to sort of understand how did the first scientists learn anything, and how did they change the way that they learned things? How did they change their framework of analysis over time as they learned that one mode was better than another? This is extremely helpful to know. So honestly, it's like Physics 101 is like if people really pay attention to Physics 101, that's the most valuable. And then, I thought quantum mechanics was really interesting too.
So there you have it from Elon Musk. Physics 101 for him was the most useful course. This course that you're in at the moment was the most meaningful course for him in terms of the way he thinks about the world, the way he thinks about problems, the way he formulates strategies from first principles. We now take a look at the SI units and what those are. So the SI units were agreed by a body in 1960, and those are the units that we're going to use in our science, in our problem solving. As shown here, there are a number of quantities that we want to describe when doing science. It could be a length, it could be a mass, it could be a time, and so forth. And shown on the right is the associated SI units. So if we're speaking about length, then the SI unit is meter. So whenever we solve problems or report scientific quantities to do with length, we're going to report them in meters. We're not going to report them in kilometers or inches or feet or any other type of units. The SI unit that we're going to use is meter. Similarly for mass, when we solve problems, when we report quantities, we're going to make use of the kilogram. Not the gram, or any other unit but the kilogram. For time, we work in seconds. Temperature, in everyday use, we make use of the degrees Celsius in South Africa. But when we work in physics, using SI units, we're going to make use of the Kelvin. Other quantities is the electric current. You would have seen that before from school, and you would have heard of the ampere. This is one that you may not be familiar with, luminosity in intensity. The SI unit for this is the candela. So perhaps when you buy a TV, an important spec for the TV is, how bright is the screen, and this would then be reported in candela. When we are referring to the amount of substance present, the SI unit for that is the mole. A mole is similar to it's 6,022 times 10 to the 23. That's the number of molecules, or the number of particles, or the number of entities present in a mole. So you should be aware of each of these different quantities and their associated SI units. This is something you should know. In mechanics, the first part of the course, the main three quantities that we're going to be making use of is length, mass, and time. The second point is quite interesting. It says you will notice that other quantities are derived from these three. It says you will also use derived quantities. These are quantities that can be expressed in terms of the other basic quantities. The example given is the area is a product of two lengths. So when we speak about area, we report it in meters squared, but area is length times length. So area is a non-SI quantity, but it can be reported in terms of SI quantity of length multiplied together. Length is the fundamental quantity. Another example would be when we speak of speed. Speed is, we report that in meters per second, and you can see that comes from a combination of the fundamental quantities of length, which gives the meters, and seconds, which comes from the SI quantity for time. Similarly, acceleration, meters per second squared. Again, it uses meters and seconds squared in the derived quantity. Something quite interesting is that each country has a physical quantity that represents these reference standards. At NMISA, which is the National Metrology Institute of South Africa, we have, for example, a block that weighs exactly 1 kg, and this is the reference standard for South Africa. It's kept in a jar, and the jar is kept under vacuum. This is to stop air coming into contact with the block, which could cause oxidization and the mass of the block to change. We also have, for example, other reference standards. We have atomic clocks, which keep the time standard for the country. What we're going to be looking at now is different prefixes. When I say prefixes, I'm referring to corresponding powers of 10. For example, if we speak of 1 milligram, then a milli, milli represented by the small m, refers to 10 to the power minus 3. So it's a thousandth of a gram. A milligram is a thousandth of a gram. Similarly, a number of prefixes are shown here. We have a power, a prefix, and then abbreviation. And you'll need to make sure that you know each of these, that you're able to remember them. If we look at this column on the right, we see we have increase in powers of 3. We go from kilo, which is 10 to the power of 3, for example, a kilometer, to mega, which is 10 to the power of 6. You would have heard of perhaps a megawatt, that's represented by a capital M. Go from mega to giga to tera to peta to exa to zeta to yotta, which is 10 to the 24. Similarly, if we go 10 down the scale in smaller values, then a centimeter would be 10 to the power of minus 2. Centi represented by 10 to the power of minus 2 100th of the quantity. A milli is 10 to the power of minus 3. Micro is 10 to the minus 6. Note in each case their symbol. And so we go nano, getting smaller, pico, minus 12, femto, minus 15, atto, zepto, yocto. So many of these powers you'll be familiar with. For example, you'll be familiar with a kilogram, kilo. You know from data, when we speak of data, the smallest, if you have an MP3 file, it might be in the order of megabits per second, if you have a hard drive, it might be, hundreds of or gigabits, in the order of gigabits. So that would be 1,000 times bigger, 10 to the 9. Very big drives can be terabits per second. That would be in the order of the data flowing around the internet. Similarly, you'll be familiar with centi, milli, micro, nano, 10 to the minus 9, pico to the minus 12. So take a look through this list and make sure that you know what each of the powers represents, as well as their abbreviation. Now we take a look at order of magnitude calculations. What are they and how do we go about performing them? Well, if you think of order of magnitude calculations, they sort of calculations that give us a rough answer based on a number of different assumptions. Perhaps you've had the experience where you've taken your cell phone in to be fixed, and you've asked the guy's taking a look at it, and he's saying, yeah, sure, come back later, I'll fix it for you, then you can get it back. And then you say to him, well, how much is it going to be to fix my cell phone? And he says, no, really, I have no idea. Just come back and then you can pay me and get your cell phone back. And then you say to him, give me some kind of rough idea. Is it going to be 10 Rand to fix? Is it going to be 100 Rand to fix? Is it going to be 1,000 Rand to fix? Maybe going to be 10,000 Rand to fix, because if it's going to be more than like 1,000 Rand, maybe I'm going to think about getting a new cell phone. So what we're asking the dealer for in this case is a ballpark estimate. Is it going to be 10? Is it going to be 100 Rand to fix? So what we speaking of when we speak about ballpark calculations or order of magnitude calculations, we want a rough answer, and the final answer that we are going to report is going to be a power of 10. Right, now we take a look at the steps for performing order of magnitude calculations. The types of problems that we're going to address, they're really very, very varied, and they may seem to you a little bit, outlandish. For example, we may calculate how many times do we blink in our lifetime. We would use an order of magnitude calculation to estimate that quantity. Or we may want to calculate how many grains of sand are there on a beach. Or one of the questions we're going to look at now is how many ping pong balls would it take to fill a room. So the first step we would need to do is to decide on a formula or method that we're going to use. So if we're interested, say, how many ping pong balls will fill a room, then a method that we might use is we might, calculate the volume of a room, and then calculate the volume of a ping pong ball, and then divide the volume of the room by the volume of one ping pong ball, and that would tell us how many ping pong balls would fit in the room. So that's the formula or the method in that case. We need to estimate, relevant quantities. So, for example, we may estimate that the diameter of a ping pong ball is, a certain number of centimeters. Then we need to also make certain assumptions in our calculation. The assumptions might be, an assumption about the size of the room. We might need to make an estimate or an assumption about how many meters each dimension of a typical room would be. Remember, for order of magnitude calculations, you're not going to be given all the information, so you need to assume some of the information in order to do the calculation. Finally, on step 4, we calculate the answer, and then finally under 5 we round it to an order of magnitude. That's to say that we leave the final answer as a power of 10. Perhaps it's going to be 100, perhaps it's going to be 10,000, perhaps it's going to be a million, maybe it's going to be 0.01 if it's a very small number, maybe it's going to be 1 times 10 to the minus 15. But these are all powers of 10. And what we're going to be doing now is we're going to be looking at the rules for rounding the final answer. So imagine we've just done an order of magnitude calculation and we've come out with an answer, and I would like to round it to a power of 10. How will we do that? And we'll do that following this recipe shown on this slide. At the bottom there are 3 examples where they show 0.0086 is rounded off to 10 to the minus 2. They show 0.0021 is rounded off to approximately 10 to the minus 3, and another example for 720. So what we're going to do is use this recipe and show you how to do the rounding. So under step 1 it says write the answer in scientific notation. So if we would like to write a number in scientific notation, then we would need to write that as, scientific notation means that we have 1 digit followed by a point, followed by a comma, followed by the remaining digits, and then times 10 to some power. So we write 0.086, we write that as 8.6 times 10 to the minus, I would need to move this comma 1, 2, 3 spaces. So it's times 10 to the minus 3 meters. That's the first step of the recipe. The second step says divide the number by the power of 10. That's another way of thinking of that is just to ignore this power for now. We're not going to look at this power, we're just going to look at the number in front, okay? And in step 3 it says compare this number in front to the number 3.162, which is the square root of 10. So every time we look at the number in front, we're going to be comparing it to this number 3.162. And we're going to use this comparison to tell us how we should do the rounding. If this number in front is bigger than 3.162, then we're going to round this number to a 10. If it's less than 3.162, we're going to round this number to a 1. That's what step 3 says. So in this case we have 8.6 is bigger than 3.162, so we write this we round it up, we round it to a 10. So this is then becomes 10 times 10 to the minus 3 meters. 10 times 10 to the minus 3, if we multiply this 10 in, we can rewrite this as 1 times 10 to the minus 2 meters. And 1 times anything is, just itself. So it's 10 to the minus 2 meters. Then is the solution for the rounding rule of the first quantity. As you can see on the bottom left of the slide, just above my head, that's the solution of it rounded. Let's apply this recipe to the second example. Here we have the second example. Well, the first step I should do is I should write it in scientific notation. So writing this in scientific notation, this would be 2.1 times 10. Again, I need to move this decimal place 3 points. So again, it's 10.1 times 10 to the minus 3 meters. That's the first step. The second step says, we should ignore this power and we should just look at the number in front. So here the number is 2.1. We should compare 2.1 to 3.162. Here we see it's less than 3.162. So instead of making this a 10, I'm going to round it down to a 1. So here we have 1 times 10 to the minus 3 meters. Again, anything times 1 is just itself. So this is 10 to the minus 3 meters. So it means that's using the rule, this number is approximately close to approximately 10 to the minus 3 using these rounding rules. The third example we have is 720 meters, If I write this in scientific notation, then it's going to be 7.2 times 10. This time it's going to be a positive power. So it's 7.2 times 10 to the 2 meters, right? The second step says we ignore this power. We don't look at the power. We just look at the number in front. Well, the number in front this time is 7.2. 7.2 is bigger than 3.162. So in this case, we're going to round this up to 10. And then we still have the 10 times 10 to the 2. And 10 times 10 to the 2 meters, that's the same as 10 to the power of 3 meters. So this is the solution then for this number rounded to an order of magnitude. If you think about it, it kind of makes sense, because what we've done is we've said 720. It's close to 1,000. So we've said to order of magnitude 720 is close to 1,000. It's certainly a lot closer to 1,000 than to 100. Now we move on to look at the solution to the problem we discussed before. How many table tennis balls can fit in a room? In these kinds of questions, it's good to know sort of the equations for calculating the volume of different shapes, possibly a sphere, a cube. In general, for different problems, it might be also good to remember the equation for density of an object as listed here. But back to our problem. We asked to calculate how many table tennis balls can fit in a room. So according to this, you'll need to make a number of assumptions, and you'll need to list those assumptions, and we'll also need to estimate different quantities. So the assumption that I've made is that the size of a room is 10 meters by 15 meters by 8 meters. So this is a really large room, a lecture hall. Of course, if you had assumed it's smaller, maybe a bedroom, that would have been fine, but just list your assumption and provide the dimensions that you've assumed it to be. Secondly, we need to estimate the size of a ping pong ball. So, a ping pong ball, it might be, I've estimated it in the order of 6 centimeters. Take a look on your ruler and see how big 6 centimeters is. See if you agree with that. It's just an estimate, right? Of course, the ball is a spherical shape, and the volume for a sphere is 4 over 3 pi r to the 3. If you think about ping pong balls, and if they're packed in a box in a room, then the shape that they actually take up is a cube. In that the ping pong balls, they will be sort of next to each other, and they will be touching each other from all sides, right? So the volume, the space that each occupies, including its little interball gaps, it'll be the shape of a cube. So for that reason, for this problem, you could just as well use the equation for a ball or for a cube. The method that we're going to use is we're going to calculate the volume of the room, and then we're going to divide that by the volume of one ball. So if I go ahead and do that calculation, the volume of the room is going to be the length times the breadth times the height. So this is going to be equal to 10 meters times 15 meters times 8 meters. The volume of one ball. So remember, it will be the length times the breadth times the height. I'm going to use this cube. Length times breadth times height. So we need to work in centimeters. 6 centimeters is 6 times 10 to the minus 2 meters. Here we convert everything to SI units. So it will be length times breadth and then times 6 times 10 to the minus 2 meters again. I ran out of space there. And if we calculate what that is, then you can calculate it for yourself, but it's actually 5,555,000. It's actually this number of balls, 5,555,000 5,055 balls. So the next thing we need to do is, round this off to the correct order of magnitude. We spoke about that before. When we want to round something off to order of magnitude, the first step that we need to do is write it in scientific notation. So this is going to be 5.5. You can count how many spaces you need to move the comma. 1, 2, 3, 4, 5, 6. We need to move it six spaces. So this is times 10 to the 6 balls, right? The next thing we need to do is we need to take a look at the number preceding the 10 multiplier. So we look at this number here, this 5,5, and we compare this to the number 3.162, the number we compare it to. And we note that in this case 5.5 is bigger than 3.162, so that means that we're going to round this 5.5 to 10. So this is 10 times 10 to the 6 balls, which is of course 10 to the 7 balls. So there, we've done an order of magnitude calculation, and our solution is written as a power of 10, and we see the solution is 10 million ping pong balls. I'd like you to look in your textbook and to look online, and you'll be able to find multiple examples of questions to do with order of magnitude calculations. Another one we can speak briefly about the solution is how many petrol stations are there in South Africa if we're asked to estimate that. Well, one way to do it could be to think how many petrol stations are there in a suburb, just in a typical suburb, in the one in which you find yourself. Perhaps you might say 6, perhaps you might say 10. You can make an estimate, right, of that number. Then you can think how many suburbs are there in a big city. Think of the city and try count them and see how many you come up with. Next we can see how many big cities are there in South Africa. Well, we could estimate that from a map. We could count them off from a map, and by multiplying these three numbers together, the first, the second and the third, you will know how many petrol stations there are in big cities in South Africa. Of course, we need to also take into account the number of stations between cities. You can estimate how many those might be. You might want to build into your model an estimate for how many small cities there are, which each maybe have 1 or 2 petrol stations. And so you can come up with a rough answer, a ballpark figure, and you can see what you get. In fact, I checked online and I found the study. They were interested in finding the 20 busiest petrol stations in South Africa, and they refer to a database of 3,155 petrol stations in their database that they considered. So perhaps the total number should be somewhere around that number. To round up this chapter, we're going to finish off by covering the topic of significant figures. The definition of a significant figure is a figure that is reliably known. That's to say, perhaps we performing a measurement. We would like to, write the measurement down, its answer, in terms of only measurements that we can reliably know. In dealing with significant figures, zeros, they may or they may not be significant, depending on their position. The zeros used to position the decimal point are not significant, and to remove ambiguity of whether zero is significant or not, we use scientific notation, and we'll see examples of that. So in a measurement, then, the significant figures, they'll include the first estimated digit. That would be in the case measurement. But let's look at some examples, then it will become clearer as we look at the examples. So remember we spoke about the zeros either being significant or not being significant. In this case we can see that we have 0.0075. It has two significant figures. These are the 7 and the 5. And we can more clearly see that it has two significant figures by writing the number in scientific notation. If you write 0.75 in scientific notation, then you can see we get 7.5 times 10 to the minus 3, which has two significant figures. 10.0, in this case the zeros are significant. The decimal point gives information about the reliability of the measurement. This final zero here, it's telling us that the measurement was 10.0 meters as opposed to 10.1 meters or 10.2 meters or something else. Whereas in this case these leading zeros, they aren't significant. In the final case, when we write this 1,500 meters, this is a little bit ambiguous because if we write it in different ways, it could have different number of significant figures. If it's written as 1.5 times 10 to the 3, it would have 2. If it's written as this, it would have 3. If it's written as this, it would have 4. Again, this would the ambiguity would be lifted by the context of in which you performed the measurement, and you'll be doing a practical dealing with significant figures and relating to measurements, and that will help make this point clearer. We have some rules for telling us how many significant figures to use when we calculate an answer. There are two different kinds of rules, or two rules. The first rule applies to multiplication and division, whereas the second rule applies to addition and subtraction. The first rule tells us when multiplying or dividing, the number of significant figures in the final answer is the same as the number of significant figures in the quantity having the lowest number of significant figures. So here we have two examples that we're going to two numbers that we're going to be multiplying together. If we multiply them out, it's 25.57 times 2.45, and this gives 62.6465. That's what my calculator says. But now I have to decide how many significant figures to write in my answer. So because I'm multiplying, what I do is I look how many significant figures does this first one have. Well, it has 1, 2, 3, 4. The second one has 1, 2, 3 significant figures. So this means that the final answer, we need to write that as having 3 significant figures, which is why we round this number off to just 62.6. So here, the 2.45 limits your results to 3 significant figures. The second rule we look at is the rule for the number of significant figures when adding or subtracting. So the rule is when adding or subtracting, the number of decimal places in the result should equal the smallest number of decimal places in any of the terms of in the sum. So remember, by decimal places we mean the number of numbers after the comma or after the decimal point. So if we take a look at this, then the example given is 135 plus 3.25. And if we take a look at the number of decimal places that 135 has, this has 0 decimal places. It has no number after a decimal point. Whereas 3.25 has 2 decimal places. When we write our answer, it needs to have the same number of decimal places as the least. And here we had 0, so we write the answer with 0 decimal places. So as we've seen then, when when dealing with adding and subtracting, the number of decimal places is the important consideration. For multiplying and dividing, the number of significant figures is the most important consideration. Finally, to round up or to finish off our chapter, we're going to look at the rules for rounding. So the last digit retained is increased by 1 if the last digit to be dropped is greater than 5. The last digit remains as it is if the last digit dropped is less than 5. So this is simply the first 2 points are if the number to be dropped is greater than 5, we round off up, whereas if we less than 5, we leave it as it is. To illustrate this first rule, if the question reads round off to 2 decimal places, then the digit to be dropped in this case is this last digit. In this case, this last digit is less than 5, so we round this off, of course, to 13.45. It's covered by the first point. In this case, if we ask to round this off to 2 decimal places, here it's greater than 5, so this will be 13.46. We round off up. The last 2 points deal with what should we do if the last digit to be dropped is equal to 5. Well, there are 2 cases. If the last digit to be dropped is equal to 5, the retaining digit should be rounded to the nearest even number. So here we can see the number to be dropped is equal to 5, and we need to round this 5 here off to the nearest even number, which is 6. So this then will become 13.46. In this case here, we see once again we have the 5, but here we can see that already this is already an even number. So for this case, we don't increase the 6, we leave it as 13.46. Alright then, this concludes the first chapter on units and measures.